Okay, we are off to chapter 9 here. We're going to talk a little bit about the liquid state. Then we'll talk a little bit about solids towards the end here. So the first thing we're really going to talk about is basically intermolecular forces and a little bit about intramolecular forces. But these are the forces that hold basically molecules together with other molecules. Also the forces that hold within a particular individual molecule things together. So let's start with intermolecular forces here. Intermolecular forces are really the attractive forces between two different molecules. And what I mean by different molecules, basically two separate molecules. I guess the better way of saying that. It can be between two of the same molecules or two different molecules. But it basically is a force that holds one particular molecule together with another. And that is the force that basically will hold those guys together in things like there's different states as well. It's responsible for the condensed states of matter like liquids and solids. Now, the intermolecular forces are responsible for things like melting points and boiling points. So as we'll talk about, sort of the stronger the intermolecular force, the higher that we see in things like melting points and boiling points. And that is because the stronger this sort of force that holds one molecule together with another means that you do need to put in more and more energy to break that bond. And that would result in a higher melting point or boiling point in that situation. Vice versa to that would be a situation where maybe you have a weaker sort of intermolecular force that's holding one molecule together with another. In that case, sort of the weaker the force between the two molecules, we would expect things to have a lower melting point and a lower boiling point. Again, that bond between the two sort of molecules, if you will, not going to be as strong, which means you don't have to put a lot of energy in there to sort of break it apart. And thus you would result in sort of a lower boiling point and melting point in that situation. So just for purposes here, we'll talk a little bit more about this in just a second. But, you know, if we took two water molecules, basically, water is a polar molecule, which means, again, the oxygen is more negative, hydrogen part's more positive. And between those two, we get this interaction that could occur between, say, the oxygen in one and the hydrogen the other. As we'll talk about, pretty much every single sort of intermolecular force is really the same basic sort of interaction that occurs, and that is basically the interaction between the positive side of one molecule and the negative side of another. So pretty much all those intermolecular forces are basically that attraction, that electrostatic attraction between positive and negative, that's basically holding those guys together. Now, this is different than an intramolecular force. Intra means within the molecule, and within the molecule is where we have our intramolecular forces. They're responsible for holding together a particular molecule. So if we went back to, say, one water molecule, for example, it is the covalent bonds here that are the intramolecular forces, the sharing of electrons between the hydrogen and the oxygen that's holding those together. So that, or something like electrostatic attraction that we see in ionic compounds, are intramolecular forces. And a sort of ionic compound, it's all those ions that are basically piled on together. You know, that's the intramolecular force. Now, the intramolecular force is usually much, much stronger than the intermolecular force. And a very simple example, or something that we're all sort of familiar with as to illustrate that, is if we go back to our sort of water and water example here, where we got a couple water molecules, again, attracted here. When we start to heat water, what ends up happening is the first bond that breaks is actually the bond right there between the different water molecules, allowing each of these water molecules basically to go off, for example, into the gas phase and make water vapor. Now, if the intramolecular force was much weaker, what would happen is, as we would heat it, these bonds would break, and we would make hydrogen gas and oxygen gas, which clearly doesn't happen. Otherwise, we would never get to the pasta making part of boiling water, right? We would just have hydrogen gas and oxygen gas that happens. So we do know that definitely that intramolecular forces, the forces within each individual sort of molecule, is always going to be much stronger than any intermolecular force that occurs. Any questions on that there? So again, intramolecular forces, things like electrostatic attraction that we see in ionic compounds, again, covalent bonding that we see in sort of molecular compounds where they're sharing electrons. Again, intermolecular forces, the ones that hold two different or separate molecules together. Any questions on that there? Okay, so what we're going to talk about now is some different types of intermolecular forces. So these are different types of intermolecular forces. And as I mentioned a second ago, pretty much all the interactions that we see are positive and negative guys being attracted to each other. So the first type of intermolecular force is what is sometimes referred to as dipole-dipole interaction. Dipole-dipole interaction happens between polar molecules. If you remember, when we talked about bonding, if something is a polar molecule, it has a dipole moment. It's those arrows, right, that we draw where it points to the more negative side of the molecule, more positive side of the molecule. So dipole-dipole forces are the intermolecular forces that basically occur when polar molecules get together. Because polar molecules have a dipole moment, what that ultimately means, as we can see in the picture, is one side of the molecule is more positive, the other side is more negative. And that means when two polar molecules basically come up on each other, what's going to happen is the positive side of one polar molecule will align itself with the negative side of the other. And now we have a nice place where there can be an interaction between those two, positive side of one, negative side of another. Obviously, in a sort of solid or liquid sort of situation, or definitely in a solid situation, they really do try to maximize that attractive force that occurs. No matter what you do, you're always going to get some negative guys near negative guys and positive guys near positive guys. But they do try to move around and sort of orient themselves as they come into sort of the solid state in a way that maximizes that sort of attractive force that we see between the positive and negative side of a molecule. So dipole-dipole interaction is basically the intermolecular force for polar molecules interacting with other polar molecules that do not have the ability to hydrogen bond. We'll talk about hydrogen bonding in just a second, but they basically do not have the ability to hydrogen bond. This is sort of the main type of way that they interact with themselves and other polar molecules. So when we talk about these intermolecular forces, we are talking about how they interact with themselves. So two molecules that are the same sort of compound, and also how they can interact with other polar molecules as well. So it can be interacting with the same molecules and different molecules as well. So obviously if we had a bunch of water molecules, you know, that's how they would all be reacting with each other. But we could also have water and something like methane that could come together and also potentially interact well with each other depending on sort of the situation. So here's what we see. Again, the interaction is this basic positive negative interaction between them. And when they get a whole bunch of them together, again, they do sort of kind of move around to maximize the attractive forces. Again, minimize sort of positive guys near positive guys. But no matter what happens, as I said, you know, you are going to get some negative guys near negative guys, positive guys near positive guys, but they try to overwhelmingly get that attractive forces together. Another type of intermolecular forces occurs when we do have ions. And this is what is sometimes referred to as an ion-dipole force. Ion-dipole force is pretty much what the name implies. It is when an ion that has a charge, either a positive or negative charge, interacts basically with a polar molecule. So this is basically what happens when we dissolve a solid in something like water, right? Water, once again, is polar, which has the positive side on the hydrogens, negative side on the oxygens. So when we put like a chloride ion into solution. The water molecules basically will surround the chloride ion at the hydrogen side, and again, all the way around. And if you put something like sodium chloride, obviously in water, the water will also surround the positive ion here, except that it's going to be the negative side of basically water that's going to do that. That once again is pretty much what allows it to dissolve and why we can't sort of see it anymore. And it looks like it's maybe disappeared or went away or something like that. And it's really because there's tons and tons of water molecules that basically surround all these ions, and it's no longer sort of visible to our eyes. It also provides a good service, as we've talked about, I think previously. It also prevents these two guys from coming back together. And that is because if they wanted to come back together, that's a very strong electrostatic attraction, sort of an intramolecular force that would pull those guys together. And that is what happens when we do, for example, take something like sodium chloride solution and we heat it up. We're going to evaporate off all those waters and then allow those those ions to come back together, and we'll make that ionic solid. So ion-dipole is really the sort of intermolecular force that occurs when an ion is present near a polar molecule. And that is why, in terms of solubility, something that is ionic and something that is polar are soluble in each other, because they can interact really well with one another through this type of interaction. Now, dispersion forces are another type of intermolecular force, and these are really the weakest of all the forces here. And this is really the type of force that is predominantly seen in nonpolar molecules interacting with other nonpolar molecules, are themselves as nonpolar and nonpolar. And there's really a couple of ways that this occurs, but an induced dipole is basically a situation where we can make a temporary dipole in something that normally does not have it. So if you remember, a nonpolar molecule basically means that it's going to be overall sharing its electrons relatively equally, which what that means is, in a nonpolar sort of molecule, there's really no side of the molecule that is positive. There's no side that's negative. It's sort of like a neutral sort of molecule in that case, because we have the equal sharing of electrons. Remember, that's different than obviously what we've been talking about here with a polar molecule. Because of the overall unequal sharing of electrons, there's a side of that molecule is more positive and a side that's more negative. So when we have this sort of neutral nonpolar molecule, there's a couple of ways we could actually induce a dipole, and one way is an ion-induced dipole. And what that means is an ion such as this positive guy here comes upon a nonpolar molecule. When that positive ion comes near that nonpolar molecule that normally does not have any type of charge, it's going to allow the electrons to be attracted to it. And what's going to happen is it's going to induce in that normally neutral guy a temporary charge is going to occur. And that's going to allow a temporary weak type of interaction to occur between the ion and the nonpolar molecule. That could also happen when a polar molecule comes on by near a nonpolar molecule. Same thing is going to happen, going to cause those electrons in the nonpolar molecule basically to be attracted to the positive side of the polar guy. And it's going to allow a temporary sort of interaction to basically occur. That is why, you know, for example, one of the reasons, like if you take something like, say, oil and vinegar salad dressing, you can mix it up, right? And it stays mixed for a little bit, right? But eventually it all sort of separates out. So over the long range, there's no way for those guys to basically keep that interaction going, and they'll eventually separate out. And it's the same thing here. These are temporary weak type forces, and eventually these electrons will sort of return to normal in each of these situations and sort of break apart that interaction that's occurring. Now, in addition to sort of a polar molecule or maybe an ion being able to slightly induce a dipole moment, there is an idea of what is referred to as polarizability. And polarizability is basically the ability at which a molecule has the ability to sort of move its electrons from one side of the molecule to another. So the nonpolar molecule, for example, and another nonpolar molecule near each other, if say the nonpolar molecule on the left there has a great ease of moving those electrons, and for some reason all the electrons in this guy decide we're all going to go vacation over here on the right hand side of the molecule because they're moving around, what will end up happening in that first nonpolar molecule is it normally will not have a charge, but because those electrons decided to go to the right there, it will now cause this temporary sort of charge in that nonpolar molecule, who, if it was happened to still be sitting next to another nonpolar molecule, will cause the electrons in this guy to go away from that negative charge and thus create a temporary charge in the second nonpolar molecule. And now these two guys that started out with basically no charge will temporarily sort of gain a charge and allows them basically to interact with each other. And this is what happens predominantly in nonpolar molecules, because this is really the only way they can interact with other nonpolar molecules is through this sort of instantaneous or temporary dipoles that basically occur. As those electrons again sort of move back into their sort of maybe normal situation, they're going to kind of break apart, and then they're going to create maybe new interactions with other nonpolar molecules. But they really can't, for in most purposes, lock all this into place because they rely upon those electrons basically moving about and getting these temporary charges. This is what is sometimes referred to as creating an instantaneous dipole, and it can just happen by the electrons just deciding kind of to move one side of the molecule or next. We have a greater ease of polarizability with a larger number of electrons. So in terms of comparison of a stronger dispersion force versus another dispersion force, if you have a compound that has a greater molar mass, that means it has more atoms, and also means it would have more electrons present, which means it would be a greater opportunity for these electrons to kind of move one way or the other. And it would create a stronger dispersion force, if you will, than something that is a lower molar mass in terms of a nonpolar molecule. And it would have actually a higher boiling point and melting point in comparison of the two sort of nonpolar guys. So the strength of dispersion forces here basically does increase with molar mass, again, because there's more electrons, greater chance of these electrons sort of moving around and creating these temporary interactions. Also, because there's more atoms present, there's more areas where these interactions could actually occur and creates a stronger sort of dispersion force. So these dispersion forces increase with those larger molecules. And again, it is basically the weakest out of them all. And it is the main thing from a nonpolar and a nonpolar interaction. Truth be told, every single person or compound can do some type of dispersion forces. So even polar molecules can do dispersion forces, which is why they're able to do that sort of temporary interaction that kind of occurs for a while. But that's not their main source of how they interact with other molecules. For nonpolar molecules, dispersion forces are basically the main way that they're able to interact with everybody. So dipole, dipole, dipole-induced dipole, and dispersion forces, all sometimes referred to as van der Waals forces, as we talked about with real gases. He did a lot of work with, obviously, intermolecular forces. Any questions on that there? So here's sort of that instantaneous dipole again, in this sort of nonpolar guy, gets this temporary sort of charge causing a temporary charge over here. And again, positive on the left, negative on the right, allowing that interaction to basically occur between those two molecules. Now, a special type of dipole-dipole interaction is what is known as hydrogen bonding. And hydrogen bonding, much like the name implies, is a type of bond that occurs between a hydrogen atom in a polar bond with an electronegative atom like nitrogen, oxygen, or fluorine. So in order for somebody to hydrogen bond, you basically need a hydrogen that is bonded to nitrogen, oxygen, or fluorine. And if you look up there on the periodic table, nitrogen, oxygen, and fluorine, these are our big three electronegative guys, right? So increase in electronegativity to fluorine. So you need those kind of atoms there to really create a very good separation of charge on that bond, and that's going to create a place where hydrogen bonding could occur. And that is the type of bonding that we do see in water. So as we talked about before, we got the negative and the positive here. And it is the bond between the negative oxygen and the hydrogen here. This guy's able to hydrogen bond because the hydrogen is directly bound to an oxygen. Now, sometimes people are confused about hydrogen bonding in the sense that they just feel like there just needs to be a hydrogen present. And if we took something like methane, for example, here, and methane here has a ton of hydrogens. But first off, all these hydrogens are pretty much non-polar bond, right? Carbon hydrogen is non-polar. These hydrogens are not attached directly to a nitrogen, oxygen, or fluorine, so it cannot hydrogen bond, even though it's got a ton of hydrogens there. So this guy really is non-polar, which means he would actually use dispersion forces. So even though something may have a lot of hydrogens in it, it doesn't mean it has the ability to hydrogen bond. That hydrogen needs to be directly attached to a nitrogen, oxygen, or fluorine in order for it to participate in hydrogen bonding. Any questions on that there? So in terms of the different types of forces, the hydrogen bonding is actually the strongest. And again, it is for polar molecules that obviously can hydrogen bond. The next sort of strongest is dipole-dipole interactions. And dipole-dipole interactions are also for really polar molecules that lack the ability to hydrogen bond. So this is polar molecules that lack the ability to hydrogen bond. And lastly here, we have our dispersion forces, which are really for nonpolar molecules. And obviously, it's that temporary interaction. So that is the weakest here. So again, how this would relate to something like melting points and boiling points. If you have somebody that has the ability to hydrogen bond, you would expect it to have the greater boiling point and the greater melting point, because it would take a lot more energy to break that stronger bond versus something that maybe just doing dipole-dipole, and definitely versus something that is doing dispersion forces that's nonpolar. Non-polar guys, again, are the weakest, which means they're using dispersion forces, which means they have very low melting points and boiling points. A lot of organic molecules are non-polar molecules, and that's why a lot of the kind of early organic molecules, they're like gases under normal conditions, like methane, propane, butane. They're very much gases because they're hanging together by these dispersion forces. That's also why when you take organic chemistry, they usually put you in a fume hood, because a lot of other organic molecules are held together by dispersion forces, which means they can be very volatile. They could go into the gas phase very quickly, and you don't want to be breathing in some of that stuff. So a lot of organic guys can very much separate out and sort of go into the gas phase, with not a lot of convincing to make them do that. They're able to do it very, very easily because they're held together by these kind of weaker dispersion forces. Any questions on any of that there? So again, something like NH3, which is ammonia, can hydrogen bond. this hydrogen is attached directly to a nitrogen, so going to make a polar type of bond, where this guy's going to be more negative, this guy's going to be more positive here. And again, it could hydrogen bond between that, say, and another ammonia if you like. So we can do its hydrogen bonding between those two things. So here is ethanol, which is an organic compound, and a lot of organic compounds, although they do have parts that are pretty much non-polar, they do possess a part that is polar. So really, if you look at something like this guy, which is ethanol, which is in this picture, this part here is really non-polar. But what it does have is this bond right here, which really is a polar bond, and is actually a pretty good polar bond because that's a hydrogen attached to an oxygen. And that allows something like ethanol to actually interact with something like water, which also obviously can hydrogen bond. And we could get some hydrogen bonding happening between those two. And that's why there are certain sort of things like organic molecules that, even though a majority of it is sort of non-polar, it does have this sort of polar aspect to it that allows it to intermolecular force and interact well with something like water, which is why it will be a little bit soluble in water in this case, and it will mix pretty well because it has the ability to interact. But like a lot of things that we'll talk about later on, you know, if you happen to build out all this part of it with lots more carbons and hydrogens, at some point that little part that's polar is just going to be sort of blocked from being able to interact well with water because of all the big other part of the molecule that gets in the way of it. Any questions on intermolecular forces here? Let's talk a little bit about the liquid state. Liquids obviously are a lot closer to one another than, say, in the gas state that we just finished talking about. So in the liquid state, everybody's packed in relatively tight to one another, but there is a lot more movement that can occur here. Molecules and stuff are able to sort of pass one another, which is why liquids are fluid. They do remain in motion. Viscosity is the resistance of a liquid to flow. It's related to intermolecular forces. So water has a low viscosity and motor oil has a high one. Viscosity does decrease with temperature. Again, increase in temperature gives everybody a little bit more energy, and they're able to sort of move past each other and sort of decreases sort of the viscosity of it. A little bit about water and some properties of water. First off, cohesive forces. Cohesive forces are the forces that of attraction between molecules of a single substance. So how a molecule in itself basically interact with each other are cohesive forces. So how water and water interacts with each other through hydrogen bonding. Adhesive forces are the forces of attraction between different molecules. And as we'll see a little later on, this is why we do see the meniscus sort of forming when we have a liquid in a glass tube. And again, in this case, the liquid is more attracted to the actual walls of the container than itself. So it causes the liquid to sort of rise up the walls of the container and make the meniscus that we sort of see. And that's why also when we read the meniscus, right, we read from the bottom of the meniscus because basically this part here just rose up the wall because of the attractive forces. It's not really where the volume actually is. If the attractive force wasn't there, those guys would come back down to basically the bottom of the meniscus, and that would actually be your volume that you actually have in there. And that's because the adhesive forces here are stronger than the cohesive forces. So the forces between the water, for example, and the container is stronger than the water versus itself. Surface tension is another sort of property of water, and it's the elasticity that's formed at the surface of a liquid. Energy is needed to expand the surface, is higher for liquids that have greater intermolecular forces. And an example, obviously, if you take some liquid, you can carefully lay sort of a paper clip on there without breaking that surface tension. But basically what happens is we have a bunch of water molecules at the surface, And what ends up happening is they are attracted to the left, to the right, and down. But there's no water molecules above them, so they're not attracted above. So it kind of pulls them to the right and left and pulls them down, and it creates that really tight surface tension that occurs. And that's different than, say, a water molecule in the center there, where it would feel basically kind of pulling in all directions because there's water molecules above it, below it, to the side. But again, without that sort of water molecules above there at the surface, it just gets sort of the side stretching and pulling down, which makes sort of the surface very, very tight in terms of it, as we see in this sort of picture here. We've all probably poured like a solution. We all poured a beverage into a cup, and you keep pouring it. It's like over the top of it, right? And you go, that's kind of cool. And then you kind of shake your hand a second, breaks the surface, and it goes all over the place. So sort of the same idea here, because these really strong interactions, for example, between water, really pulls these guys to the left, to the right, and down very, very tight, and creates that tight surface tension that we see at the beginning or the top of it. Now, there is a way that you can sort of break something like surface tension, and we do it like when we add soap and we're like washing our car. Soap basically has two parts. Soap has a nonpolar part, which is sort of a lot of times this wiggly part, which are all, really just all carbons and hydrogens, and that's nonpolar. And it also has a part that's actually polar, where it has a carbon-oxygen double bond and a negative charge here. And that's why soap is really good, because most dirt is nonpolar. And that basically means that when you have something like dirt, basically the nonpolar part of soap basically surrounds it. And all these squiggly lines are basically carbons and hydrogens. And what it does, it creates sort of a micelle where it sort of traps all the dirt on the nonpolar side of it. But on the outside of the soap molecules, we have the polar side, which is really good, because we usually, when we use soap, the next thing we do is use water, right, to wash it off. And water is polar. So as you wash off with water, the water and the polar side of soap will interact really well with each other and wash off and mix, and obviously take the dirt with you when you're doing it. We could also, for example, if you do put sort of water on something, that strong surface tension prevents the water from sort of spreading out on nonpolar surfaces, because nonpolar and polar really don't interact very well. So if you have a car, especially if you wax your car a lot, when you put water on it, it basically kind of bubbles, right? It makes little bubbles and stuff like that. The water really doesn't spread out, which is why usually when you wash your car, you wet it first, and then you take some soapy water, right? And you do that, and it allows everything to kind of spread out. And that's because the soap basically gets in between the different water molecules here, and it breaks that sort of surface tension and allows the water basically to spread out, because the polar side of soap can interact with the water there at the surface, and it allows it really to spread out. Obviously, we could wash it and then dry it and all that good stuff when you do that. Also, if you ever, they used to have an old commercial like liquid soap for like your dishes. They have the dirt on it, they do a drop of it, and then like everything just kind of spreads out. And that commercial, I think it was Dawn or something, soap or something like that. But the same idea here. When you put the soap in that water, it allows it all to kind of spread out, and it allows it to really be clean and stuff like that. So adhesive forces, as we talked about, and cohesive forces, that adhesive forces between different substances. And that's what we see when we have a glass with a small diameter and we put something like water in it. It will rise due to capillary action, and the water forms hydrogen bonds with the oxygen in the walls of the container, and it'll sort of rise it up. So you can have little capillary tubes kind of open on one end, close on the other, and it will actually sort of just naturally, through capillary action, draw up that solution, because there's a stronger attraction between the water and the glass tubing there, and it will allow the liquid to rise in it. As I mentioned a second ago, that is also why we do see the meniscus form when we do put something like a liquid. Now, not always is the attraction between the molecule and the glass container always stronger. Sometimes cohesive forces are stronger, and that actually happens with mercury, although we don't see mercury too much anymore. but old barometers and stuff, mercury actually would have sort of an upside down meniscus, and we would actually read from the top of the meniscus here in the case of mercury. And that is because the attractive forces between mercury and itself is stronger than the attractive forces between mercury and the glass tube there. And mercury basically goes in on itself and causes that upside down meniscus to occur. Once again, in this case, we read from the top because really this is an artifact of that attractive force. And really at the top there is where our actual level would be. And as I mentioned earlier, we read from the bottom of the meniscus in most cases, because the rising here is this is just an attractive force and really not where the volume actually is in that particular container. So the guy on the left there, the adhesive forces would be greater. Guy on the right there, the cohesive forces would be greater. And we see it's sort of inverse of that. Let's talk a little bit about vapor pressure. Vapor pressure is the pressure above a liquid. So the tendency for a liquid to vaporize is known as volatility, and something is really, really volatile. As I mentioned earlier, it really could go into the gas phase pretty simply. So it's something that's able to go into the gas phase very, very easily. It increases with temperature because really increasing the temperature increases the energy and allows people to kind of move into the gas phase as well. Liquid in an open container will evaporate completely because air diffuses away most of the gas molecules and prevents them from re-entering the liquid. So basically on any surface of a liquid, you have this constant guys escaping the liquid phase and basically dropping back down into the liquid phase. So you have evaporation and condensation sort of occurring at the surface of any liquid always. So they're always sort of happening this. So for example, if we think about, if you had spilled a small little sort of spot on the counter or something like that, you're going to have a lot of evaporation that's going to occur here. And what's going to happen in this situation, so it's spread out pretty good there. Again, air is going to kind of blow some of these guys away, which is not going to allow them to drop back down into the liquid part. And eventually, right, your little sort of drop there will sort of evaporate away. If you take the same sort of water, but you put it in a container, you will get some evaporation occurring, right? Again, some of these guys will get to the surface and be blown away, but you'll still have guys dropping down, but there's a lot more guys sort of trapped on the bottom that's got to work their way up, right? So it takes a lot longer for a solution in an open container to start to completely evaporate because of that. It's not as spread out, obviously not greater surface area that you have, say, if you just dropped a little bit on the counter and stuff like that. So the pressure of the vapor present at equilibrium is called the vapor pressure. So because at the surface of any liquid, you got that evaporation occurring, and you also have the condensation occurring where it comes back into liquid, they're going to reach equilibrium, which basically means the rate at which it jumps out of the solution will equal sort of the rate at which it comes back. And obviously, since we have guys leaving the liquid phase basically into the gas phase, that is going to create gas molecules above the surface of the liquid. And with gas molecules, that is basically going to create pressure above the surface of the liquid. And that is what is known as the vapor pressure. Now, this is affected obviously by intermolecular forces as well. So the weaker the intermolecular force, that means you're going to have a lot more people jumping out into the gas phase. And that should create a lot more gas molecules above the liquid of the water, for example, or solution. And that should create a higher vapor pressure. The stronger the intermolecular force is going to keep those guys in the liquid phase a lot longer. Less of them are going to travel up into the gas phase above the surface of the liquid. And that would create a lower vapor pressure because of that. Any questions on that? So when we look at a liquid in a closed container, obviously in a closed container, what you basically do is sort of prevent the escaping of that liquid. So we typically, if you put a lid on your container, won't see it evaporate off completely, right? It prevents it. But what you will see if you kind of look at it sort of closely in a lot of cases is when you first sort of put the lid on the container and you got the liquid in there, what you're going to have is a greater rate of evaporation that's going to occur. So you got these guys jumping out of the liquid phase into the gas phase. Clearly, in this case, because there is sort of a lid on the container, there's really no place for it to go. So eventually these guys will start to drop back down, and you're going to increase the rate of condensation that's going to occur. And what you'll typically notice is at the time it reaches equilibrium, which again is basically the rate of evaporation and condensation, the rate will equal each other at equilibrium. You will see that probably the liquid level will settle a little bit lower than where it started with, as obviously some of those liquid molecules have now escaped into the gas phase, and you got this sort of constant amount of gas guys above the liquid. All these guys are now in the gas phase is going to cause the vapor pressure above the liquid here. Any questions on that there? So you could actually calculate the vapor pressure if you were interested in that. Calculate the enthalpy of the reaction, or the temperature that occurs through the Clausen-Clapeyron equation here. So this is the natural log of our vapor pressure at one temperature divided by the vapor pressure at another temperature. This is the enthalpy that we talked a little bit about way early on here. The enthalpy, again, is the heat of a reaction. And that's the delta H of vaporization. So the delta H of vaporization is the energy required to go basically from the liquid state to the gas state, or backwards, basically. R is the gas constant, and it is the 8.314 version of it, since this deals with energy. So this is the guy that we use. Temperatures here does need to be in Kelvin, like all the other sort of formulas here. So again, if you know a couple of things here, you could plug and chug into here looking for what you are looking for, what it may be, a temperature, vapor pressure, or even the enthalpy of this one. So here we have the vapor pressure of water is at 25 degrees is 23.8 torr, and the heat of vaporization at 25 degrees is 43.9. Calculate the vapor pressure of water at 65 degrees. So we could do some labeling here. I see an answer there. So let's see, we got T1 here, which would be 25 degrees Celsius. That would go with our vapor pressure of 23.8 torr. Our delta H of vaporization is 43.9 kilojoules per mole. And we want to calculate the vapor pressure, our second vapor pressure. And obviously our second temperature here is 65 degrees Celsius. So we could use our equation that we saw on the previous page, which is our natural log of P1 over P2 is equal to the delta H over R 1 over T2 minus 1 over T1, I believe. Right. All right, so if we put these guys in, we do have to do some conversions. So we do want to convert that guy out to 298 Kelvin by adding our 273. We would also want to convert our 65 into Kelvin as well. So plus the 273 gives us 338 Kelvin. We could actually leave our pressure in torr. It just means our answer is going to be in torr as well. So we could okay leaving that. So we're going to go with the natural log here of our P1, which is 23.8 torr, divided by our P2, which is what we're looking for, equals 43.9 times 1,000 joules. So you may be asking, why am I multiplying by 1,000? I am multiplying by 1,000 to convert it into joules because the R underneath it is in joules. So it's a very common mistake. People leave the top guy in kilojoules, bottom guys in joules, and they're off by like that factor of 1,000. So at some point you got to do a conversion, so you can convert the kilojoules into joules, or you can convert the gas constant into kilojoules, but you got to do that conversion, otherwise you will be off. So you want to watch the units here. have to make sure that they do cancel correctly. That'll give me 1 over our second temperature, which was 338, minus 1 over our initial temperature, which was 298. I'm going to clean up everything on the right-hand side here, I think. So that's going to give me 1 divided by 338 minus 1 divided by 298. I'm then going to multiply that by my 43.9 times 1,000. I'm then going to divide that by 8.314. And let's get somewhere to the right here, I think. Clear out some mess here. All right, so kind of cleaning up the right-hand side here. Looks like I end up with, just to make sure here, 1 divided by 338 minus that. I believe I end up with minus 2.0969 on the right. Natural log of 23.8 divided by P2. To get rid of the natural log, you got to take E of both sides. So when you take the E of this side, it just becomes 23.8 divided by P2. And if you do the E of that side, if I can find it on this calculator, there it is. Try that. We end up with 0.12283. So we want to obviously solve for our guy here. So we're going to multiply P2 to both sides. Then we're going to divide by this guy to both sides over here. So that's going to give us 23.8 divided by 0.12283 is equal to P2. And that does give us a P2, I'll just go right here, of about 194 torr, about 193.756. That's what you end up with there. Any questions on that calculation there? So if you use this equation, again, the couple key things you just want to watch out for, which are common mistakes, like I said, is with that delta H being in kilojoules and R being in joules, it's those units. And then obviously normal, like everything else, temperature into Kelvin is again another common mistake that people make. Any questions on that calculation there? Now, in this case, we do see that the vapor pressure here did increase with increasing temperature, and that does make sense. As we increase the temperature, that should allow a lot more molecules to go into the gas phase, and that means we should have more molecules above the liquid, which should cause a greater vapor pressure than what we see at a lower temperature, where they have less energy to sort of escape into the gas phase in this case. Any questions on that? All right, so let's talk a little bit about some of these processes we have with liquids. The first process is boiling. So when liquid water is heated to high temperatures, bubbles of water vapor start to form beneath the surface of the liquid. When these bubbles are able to sort of escape, that is when it is boiling. That is basically when we actually see bubbles actually work their way up to the surface. It's bubbling, it's bubbling, it's boiling. You'll also probably notice right off the bat that if you hit like some water with some like heat really quick, you'll see all these sort of dots and bubbles that sort of occur really quickly. And that's not obviously the solution boiling, because you could put your finger in there and it'll be like ice cold still. But that's basically the heat at that point makes something like carbon dioxide less soluble in the water. And that's what you see sort of come out really quickly at that very first part where you hit it with the sort of flame right at the beginning. But it's really not until enough energy is built up, because basically what you have in these bubbles of boiling water, for example, is water molecules. And at some point, the water molecules, you'll have enough water molecules in there basically to equal the atmospheric pressure that's pushing down on it. And that will allow it basically, or even greater than that, to get to the surface where it will kind of pop and release basically the water as steam. Before that, you'll sometimes see bubbles start to form, right? And then they kind of pop before they get to the surface. And that's because within that sort of bubble, it doesn't have enough pressure to withstand the atmospheric pressure pushing down on it. So it sort of pops before it gets to the surface of the liquid. So at the boiling point of a liquid, the pressure of the vapor in the bubbles is equal to or greater than the sum of the water and the atmospheric pressure. So it's able to stay intact until it can get to the surface. Again, below that, it will sort of collapse. The temperature at which something boils does depend on temperature and pressure. So you could play with the pressure and stuff like that and get something to boil at maybe a lower temperature than it normally would under normal conditions and stuff like that. Boiling point, right, is typically where we go from the transition of liquid to gas is basically the boiling point. It's also really going the opposite direction, going from gas back to liquid. And as we talked about with intermolecular forces, something that has a very strong intermolecular force will have a higher boiling point than something that has a weaker intermolecular force. So something like water will have a definitely higher boiling point than something that's like an organic compound that would be using dispersion forces. So raising the pressure does increase the boiling point. So that's sort of what happens in a pressure cooker. You pop the lid on there tight, right? And the cooker holds all the pressure of the vapor above the water, resulting in an increase in the boiling point. So all that vapor above it has nowhere to go. So it gets sort of trapped into that solution, allows it to sort of boil at a higher temperature to sort of combat that. And obviously you could cook your food maybe a little bit more what you're looking for. One odd thing that sometimes people maybe don't consider about boiling is actually a cooling process, even though we think about it as being very hot, right, and fire and all that kind of stuff. But boiling is cooled as fast from the top, basically, as it is heated from the bottom. So although we are heating something from the bottom here and we're getting everybody to boil, once it gets to the top there, we are actually cooling the solution because those fast moving molecules that have moved through the liquid have now escaped into sort of the environment and they're no longer sort of in the solution. That is why when you put a thermometer, which looks like a pen, into a solution, and then it only has like 104 degrees or something on the top of the thermometer, people get nervous when it starts to boil because they consider like temperatures moving, will continue to move as you continue to boil. When you reach the boiling point, does the temperature continue to move? It doesn't, actually stays there. Yeah, and it stays there for this reason, because when you hit 100 degrees, for example, in an ideal situation, it will continue to boil at 100 degrees because just as fast as you heat the bottom, you're kind of cooling it from the top, and it keeps the boiling point right there at 100 degrees, which is why you don't have to worry about breaking your thermometer in most cases, because it shouldn't be going that high. Something you might have experienced as well, maybe through labs as well, is, it doesn't always boil at 100 degrees, right? So for example, maybe 90 something where you got some boiling happening and stuff like that. So again, the pressure is an aspect of that, based on that. So although we kind of think of boiling as being hot and a sort of heating process, it actually is a cooling process, as we do sort of cool it down from the top as we're heating it from the bottom. I'll talk a little bit about liquid in the gas phase. The process, obviously, of converting liquid molecules into the gas molecules is the process of evaporation or vaporization. It is an endothermic process. Again, heat and energy needs to kind of be put in. And what that allows is for those guys, basically, it takes some energy to kind of work your way through all that liquid so you could escape out the top there. So it takes a lot of energy to kind of move through that. And you could help that along, obviously, by heating it, which is providing that energy through the bottom there. Condensation is the opposite. Once these guys escape, they are moving a lot slower. So, they may fall back down and not have enough energy to maintain themselves in the gas phase, and they'll fall back into the liquid phase. And that's an exothermic process. They're going to release that energy. At the surface of water, there's a constant, as I mentioned before, exchange occurring between sort of liquid and gas. Evaporation and condensation at any surface is always occurring, as we talked about. And again, at some point it may reach equilibrium. The rate of going up and down may equal each other, especially in a closed sort of situation. Now, as liquid molecules escape the liquid phase, they take their kinetic energy with them, and they actually will sort of lower the kinetic energy of the liquid water, and it is cool. So as I mentioned before, as they sort of escape out the top, all that energy is leaving from the top of your boiling water there and kind of cooling it down. In addition, as I mentioned, a lot of that energy is needed to escape the liquid phase. So those escape water molecules lost a lot of kinetic energy, needed to break free from all that hydrogen bonding in the liquid phase. So actually, when they kind of move into the air, they're actually moving a lot slower, and they're sort of cooling down the air as a result of that in terms of kinetic energy as well. So overall, what we see is sort of a cooling process that occurs. Now, water cools, the evaporation rate sort of increases. That is why we sort of sweat, for example, as well. If you have water on your skin, you're going to have a great increase in evaporation of the water on your skin. That is why you feel cold, like when you get out of the pool or something like that, you got all the water on you. So you got lots of water molecule. Your skin is providing all the energy to sort of evaporate all that water, and you end up feeling very, very cold. That's also, again, like I said, why we do sort of sweat as well, right? As we start to sweat, that's going to increase that evaporation process and is going to sort of cool us down in that situation. So evaporation is sort of a cooling process when we do that. Now, at the surface of the water, condensation and evaporation is occurring. Condensation occurs when, again, those slower moving sort of water molecules collide, they stick together, and they kind of fall into the liquid. Fast moving water vapor tends to bounce off one another at the surface, but when those slow moving water molecules that don't have a lot of energy, they will start to sort of clump and sort of do that. So in addition, you're removing those slower moving water vapor molecules, which means that you are increasing the kinetic energy water vapor, and it starts to warm. So condensation is sort of a warming process, and you can feel that as well. For example, in the shower, when you're taking a shower and you have hot water creates steam. Steam then goes through condensation, which is why the mirror gets all wet, right, as you're showering and stuff like that. That's a lot of condensation happening in that room, and that is all exothermic, which means that energy needs to go somewhere, and that energy is going to you, and you feel nice and warm in that situation, right? Until you're done with your shower, you shut it off, and you've now open the door, decreased the rate of condensation a lot. You've now increased the rate of evaporation, which is then why you feel cold afterwards, when you have the water on your body in that case. So condensation is a warming process. And again, evaporation is sort of a cooling process in that sense. So there is a specific amount of energy, although we don't talk a lot about energy in here, but there's a specific amount of energy that's required to do nothing more than actually just change the phase of something. And the delta H of vaporization, which is the enthalpy of vaporization, is basically nothing more than the energy required to change a substance from liquid to gas or gas to liquid. Remember that evaporation and condensation basically occur at the same temperature. So that happens at the normal boiling point is when this happens. So because it happens at the same temperature, the delta H of vaporization is the same number. So we're not changing the temperature. We're just taking something from liquid to gas or gas to liquid. So for example, at 100 degrees Celsius, which is the normal boiling point of water. We have that process occurring. We have evaporation occurring, going from liquid to gas, and we have condensation occurring at the exact same temperature. The difference is, in terms of the energy, is really the sign. It is an endothermic process, so it would be, in the case of water, positive 40.7 kilojoules per mole, which is approximately 2,260 joules per gram. And it would be a positive number, as energy needs to be put in to do that. If we were going the opposite way, taking some of those gas molecules back to liquid, it would be negative 40.7 kilojoules per mole. Remember, negative in terms of energy is an exothermic process. Positive value is an endothermic process in this case. So it would be negative 2260 joules per gram approximately. That is a lot of energy, and as we'll see in a second about sort of the transition between freezing or solid and liquid, it takes a lot more energy to do this transition because you're completely breaking everybody apart into the gas phase. Requires a lot more energy to do that, so it's always a lot more energy to do that. These numbers that we see here are specific for water. If you're talking about some other substance would have a different value in most cases for the delta H of vaporization, and they would also have a different value in a lot of cases for the actual boiling point. So not every substance boils at 100 degrees Celsius. This is the example we use a lot, which is for water. So I sort of touched upon this again. That's again why you do feel warm in the shower, but cold when you step outside. Again, during the shower process, a big rate of condensation occurring, releasing all that energy. When you stop your shower or even get out of the swimming pool, you got a greater rate of evaporation, which makes you feel very, very cold in some cases. So let's talk about the other transition, which is freezing and melting. And obviously, freezing and melting also occur at the same temperature. For example, for water, it is 0 degrees Celsius where that occurs. That's the normal melting point or freezing point. Melting occurs when substances in the solid state basically gain enough energy to sort of start moving past each other and go into the liquid phase. And freezing occurs obviously when they release enough energy that they kind of clump together and they no longer can sort of pass one another. So once again, this process does occur at the exact same temperature. And really at that temperature, much like what we see with liquid and gas, you kind of have both phases there at the same time. And what I mean by that, for example, with something like water at exactly 0 degrees Celsius, you have kind of like ice crystals. So you got a little bit of solid there, you got some liquid happening. It's really not until you get a little bit above 0 degrees Celsius that you get liquid water. It's not until you get a little below 0 degrees Celsius that you get sort of really ice. But exactly at sort of 0 degrees Celsius in terms of water, you have basically both phases in equilibrium with each other. And that's the same thing that actually happened previously, what we were just talking about between liquid and gas. So exactly at 100 degrees Celsius, you got both phases sort of happening, liquid and gas happening at the same time. So to get water at 0 degrees to form ice, we do have to release the energy, and obviously we need to apply heat and energy. One sort of special aspect, though, of water, which is different than a lot of substances, though, is as we do release the energy here in the process of forming solid water, which is basically ice, because these guys are hydrogen bonding together here, we end up with a lot of this open space that ends up happening between the different water molecules. And that gives waters a very unusual property that a lot of substances don't have. And that is, in the solid version of water, it's actually less dense than the liquid version. That's why our ice cubes float in our water and stuff like that, right? And that's because we have a greater amount of volume in the empty space between the water molecules. And density is mass divided by volume, which means all that empty space creates a larger volume. and that would make the density of solid water less than liquid water. Any questions on that there? Now, the last couple of transitions that occur with sort of substances is the transition that occurs, which is known as sublimation or deposition. Sublimation is the process where we go from solid directly to gas. We skip the liquid phase. And deposition is going from gas back to solid, skipping the liquid phase. So that's sublimation, and that is deposition occurring here. So an example of that is something like dry ice, which is carbon dioxide. So dry ice, if you've used before, very, very cold. But under normal conditions, dry ice will go directly from the solid state into the gas state, no liquid cleanup in between, but very, very cold as well. Deposition, although they don't make too much of these things anymore, like CDs, DVDs, they're really shiny. That process of deposition, dropping metals on top of the surface of those discs, that's what kind of gives them that shine and stuff like that. And that's the process of deposition. Same idea, going from solid to gas is an endothermic process. So it'll be positive delta H, putting in there our energy. Going from gas back to solid, you have to release all that energy and then be an exothermic process. Now, the molar heat of fusion, or the heat of fusion, is the energy required to do the transition between solid and liquid. So the delta H of fusion, it is sometimes referred to, is that energy needed to go from solid to liquid or backwards for a particular substance. Again, it happens at a specific temperature. The number we see up here is actually for water. So delta H of fusion for water is 6.02 kilojoules per mole, or approximately 335 joules per gram. And it's the same idea as we would go from solid to liquid here. This would be positive 335 joules per gram. And if we go from liquid back to solid, be negative 335 joules per gram to do that. In comparison, as we just saw a little bit ago, the heat of vaporization, the delta H of vaporization, which is a transition between liquid and gas, was about 2260 joules per gram. So once again, you can see there is a big difference in energy as you go from liquid to gas. Much more energy required to do that than going from liquid to solid or solid to liquid. And that's because in the solid state, everybody's still packed pretty tight to each other. In the liquid state, they're still packed pretty tight to each other, but there's a little bit more room for movement, but they haven't really completely sort of separated from each other. And that transition is what occurs as we go from liquid to gas. And that's why we see a much higher amount of energy required to do that transition. Same idea here as what we see here. Again, as I mentioned, you have ice crystals at exactly 0 degrees Celsius. This is what is sometimes referred to as being in equilibrium with each other at 0 degrees Celsius. You have both phases happening at the same time. Any questions on that? So this is a heating and cooling curve. And again, it shows us that this is for water. Heating going from ice, which is the solid version, to obviously liquid water, to steam, which is the gas version here. Now, when we look at this sort of graph here, there's a couple of spots. Right here is for water. This is our normal boiling point. Down here is our normal freezing point that occurs here. And that's at 100 degrees Celsius. This is where our delta H of vaporization would come into play. You can see it's a plateau line, which means it stays at 100 degrees all the way across. Over here, going from solid to liquid, this is where our delta H of fusion would come into play. Once again, it's a plateau line, which happens at exactly 0 degrees. So on those highlighted lines there, you have both phases happening at the same time, not to get a little bit above and so forth. To calculate the other parts, where we look at this, for example, coming from 0 degrees Celsius to 100 degrees Celsius, all through this green line here. That is all the same phase. That is all liquid water all the way through there. If you went from 100 degrees Celsius to whatever that is, 140 degrees Celsius, that is all the same phase. That is all gas going through that line. And if you went below 0 degrees Celsius to like minus 20 on this graph, that is all basically solid. In those transitions, it's different than the transitions of delta H of vaporization or delta H of fusion. In vaporization or fusion, we are going from one phase to the next. In those green lines, we are all keeping basically the same phase. You could also calculate the heat associated with that, but to do that, that is what is known as specific heat, is what you would actually use. And it has an equation of Q is equal to ms delta T. Q is the heat or energy, and that's usually in joules or calories. M is mass, which is usually in grams. S is the specific heat capacity. And that usually has units of joules per gram per degree Celsius or calories per gram per degree Celsius. And T is the change in temperature, which is our final temperature minus our initial temperature. And it is one of the few things in chemistry that you actually could leave it in degrees Celsius. So we would use that equation to figure out the heat or energy for those transitions. And you'll do that in 200B nowadays. They take it out of this class, but you'll go back and learn about that in 200B. But that's the way we could actually calculate the heat or energy going in those transitions. So anywhere where the phase basically stays the same, but you change the temperature, that's more of a specific heat type calculation. And anywhere where basically the temperature stays the same, but the phases change, that's a heat of fusion, heat of vaporization type situation that's occurring. Any questions on that there? Yeah. It is. Some books use S, some books use C, some books use SH. Yeah. The specific heat capacity is basically the energy needed to raise 1 gram of a substance by 1 degree Celsius. And that's basically the definition of specific heat capacity. But yeah, some books will use C for specific heat capacity. Some books will use S, and some books will even use SH for specific heat capacity. But they're all basically the same. You might, if you use this maybe in the pre-class, you usually do this type of stuff. That's that where that 4.184 joules per gram per degree Celsius or 1 calorie per gram per degree Celsius. That's the specific heat capacity for liquid water. So that's a specific heat capacity, and that's a very common number. Sometimes people see a lot. We're going to do that. Other questions on it? So we won't do obviously any calculations involved in that. You'll do it in 200B nowadays, even though it's chapter 6, I think, in the book and stuff like that. So you guys will come back to that. But since they assume you probably read the book, they might mention something of it in this chapter. So we're going to talk a little bit about phase diagrams here. Phase diagrams are a diagram that basically shows the 3 phases of a substance. That would be solid, liquid, and gas. And also the 6 inner conversions among them. In case you're curious, the 6 inner conversions are solid to liquid, liquid to gas, solid to gas, and backwards. Yes. So those are the 6 inner conversions: solid to liquid, which is melting, or liquid to solid, which is freezing, liquid to gas, which is evaporation, gas to liquid, which is condensation, solid directly to gas, which is sublimation, and gas directly back to solid, which is deposition. There's also the temperature and pressure values associated with that. We'll see here in just a second. There's a part on that which is sometimes referred to as the triple point, and the triple point is the temperature pressure combination for that particular substance where you have all 3 phases happening at once. So it's like your temperature pressure combination where you have solid, liquid, and gas all sort of occurring at the same time. Water has an unusual sort of phase diagram. It has a negative slope. And again, that's because you see, as we talked about, less dense than liquid water. A couple other important points on a phase diagram, which we'll take a look at in just a second. There's what is referred to as the critical temperature. And at the critical temperature, that is the point where there's really no distinction between the liquid phase and the gas phase. It's sort of where that substance kind of flows together, and it has properties that are liquid but kind of flows like a gas at that point. So there's a temperature pressure sort of part where that occurs. That's also the critical pressure also occurs at that point, where there's again no distinction between that liquid and vapor pressure. It's also sometimes those 2 points are sometimes referred to as the critical point, where the temperature and pressure basically allows the liquid and vapor part basically to kind of flow together. At that point or above that point, where you have that critical point, that is sometimes referred to as a supercritical fluid, and that is a one where it has the density of a liquid, but it does have a lot of properties and sort of flow like a gas at that point. Take a look at a generic sort of phase diagram. It looks like this. And typically this is sort of the setup where we have our solid, liquid, and gas sort of phases on it, where our pressure and temperature. And we have this line, which is our melting point curve, where as we cross over from solid to liquid, that is melting. And as we cross over from liquid back to solid, that is freezing. Going from liquid to our gas, again, as we cross over from our liquid to our gas, that's evaporation. Coming back the other way, that would be condensation. And if we come way down here on the bottom of the curve here, crossing the line on the bottom takes us from solid directly into gas. So that is our sublimation occurring. And if we go from the bottom back from our gas directly to our solid, that is deposition that's occurring. If you hit, for example, we'll say this was 1 atmosphere, which is our normal pressure. If you go across and hit where that is, right on that line, that would be the normal melting point that would occur at that point. If you continue across, right here would be the normal boiling point that would occur at 1 atmosphere. And you could go down and figure out at what temperature we're talking about in that situation. There's the triple point right there, which is that point that I just scribbled all over. That point right there is where all 3 phases are basically happening at the same point. Up here between the liquid and the gas line, at the end of that line is the critical point, and that is where we have our critical temperature and our critical pressure. So above that point, that's where we get our supercritical fluid. And you can see it's kind of open. So at that point, really the liquid phase kind of flows into the gas phase at that point. And that's why, again, we have somebody that has sort of properties of gases and also liquids as well that occurs. Any questions on any of that there? So you do need to know, obviously, what one of these look like. We're going to do some more examples of it next time, but where solid, liquid, and gas is, where the different sort of phases occurs, the triple point and the critical point. Any questions on that? All right, we will lay it up there for today.